So hello everybody, I'm working here in KIT and I will make a complementary talk about biophysical effects of land use and land cover changes. So it will be 1 hour today and maybe 1 hour tomorrow. But before that, maybe we should agree on some acronyms and definitions used in this presentation. So the land use and land cover changes, LULCC, are defined by two things. The land use change, it's how the people are using the land. And land cover changes, it's how physical land type changes, naturally or not. The R5, it's the most recent IPCC assessment report in 2013. And the CEMIP 5 models are the most recent state-of-the-art global coupled models from the R5. As maybe all of you know, the albedo is the fraction of reflected sunlight, so it's very high for snow like in Garmisch today, and very low for forests. So Joe this morning and Tom also talked about the biogeochemical effects of land use and land cover change, but which can be summarized as the alteration of the carbon cycle due to land use and land cover changes, through photosynthesis changes, respiration changes, decomposition, CO2 fertilization, etc. But here I will only focus on the biogeophysical effects, which can be summarized as the alteration of not the carbon cycle, but the water and the energy cycles through the alteration, the modification of physical land surface characteristics. So changes in albedo, changes in roughness length, changes in evapotranspiration efficiency, deep rooting, and so on. So the land use and land cover changes are modifying the biophysical property, altering the radiative balance, essentially through the albedo, the water balance through the evapotranspiration efficiency, and the momentum balance through the changes in roughness length. So go on first for the surface energy balance and some equations that you will find useful for this afternoon with the practical with Tom. So the surface radiative balance, here Rn is the net radiative, the net absorbed radiation at the surface. So that's the input shortwave incident radiation coming from the sunlight. And as input, we have also the incident long wave, which depends on the temperature structure of the atmosphere, the humidity structure, the cloud cover, but also the gas, greenhouse gases concentration in the atmosphere, minus the emitted radiation. So shortwave, the outgoing shortwave can be expressed as the product of the albedo and the incident shortwave. Here I gave some values, typical values for albedo. So it's between 1 and 0. And the fresh snow, it's one of the land conditions that gives the highest value for albedo, 0.9. You have the clouds, depending on if they are low clouds, big clouds, high clouds, but they are quite bright, so an albedo between 0.4 and 0.7. And after you have dark land conditions like grass that have 0.2, 0.3 for an albedo, but still higher than a forest, which is a dark conditions for the land. Yes, for the outgoing long wave radiation, it's expressed in function of the Boltzmann law. So the outgoing long wave radiation is proportional to the surface temperature raised to the 4th power. And the surface radiative balance leads to the surface energy balance because the absorbed net radiations is afterwards released to the atmosphere through the surface heat fluxes, and mainly two of them. The latent heat flux, lambda E, which is proportional to the evapotranspiration. We call it latent because there is no phase changing. The water still remains liquid. And when you have a phase changing in the atmosphere, for example, condensation, then the heat will be released. So we call it latent because it occurs later. And the sensible heat flux, so SH, that warms directly and immediately the layers of atmosphere above the surface by conductions. And one order of magnitude less, we have, in general, the ground heat flux, that is heat flux by diffusion in the ground. So at equilibrium, we have the absorbed net radiation that is equal to the sum of these three fluxes. So the net absorbed radiation is released through the surface heat fluxes. And the two main fluxes here, SH and lambda E, the sensible and latent heat flux, are driven by the gradient of the quantity considered. So the sensible heat flux is proportional to the temperature gradients between the surface and the free atmosphere. So we will see after what is it. And for the latent heat flux, it's proportional to the humidity gradient. We express also the ability of the physical land type to resist to the release of these fluxes through the aerodynamic resistance. And you see that when this resistance increases, then the release of fluxes is less easy, so it's decrease the fluxes. So the interaction with the surface generates turbulence, and this turbulence takes place into the planetary boundary layer, which is the portion of the atmosphere in which the wind flow is strongly influenced by the surface. So you can say that above, just above the planetary boundary layer, then the wind flow is not anymore influenced by the surface. And this turbulence plays a major role in transporting the heat and the water vapor away from the surface. Let's see now the characteristic of roughness, and RA, it's the aerodynamic resistance. So it's basically related to wind speed, atmospheric stability, and surface roughness. So when you increase the wind speed, you will favor the release of the fluxes through turbulence. So the resistance of this physical land type will decrease. When you have now increased atmospheric stability, it means that the gradient of temperature and humidity are smaller, so it will be more difficult to release the surface heat fluxes, so the resistance is increasing. And finally, if you have, for example, a forest compared to a grassland, there is an increasing surface roughness length, so it's easier to exchange with the atmosphere through the leaves, through the canopy, etc. These fluxes, so the resistance of the physical land type decrease. So you have a very low value of roughness, of aerodynamic resistance for forests. As you can see, 5 between 10. And for grass, you have roughly 10 times higher aerodynamic resistance. And between them, you have the crops that can be assimilated to grass from a biophysical point of view some month of the year, and a mini forest during just before harvest. So that's logical to have this value between grass and forest for crops. So I talked about the surface radiative and energy balance that are affected by the changes in land use and land cover change. But there is also the land-water cycle that is affected. And this is a very talkative figure from Bonan, which shows that for a given input of water, so let's say precipitation minus evaporation, of 100 millimeter, with a forest land type, then the majority of the water is infiltrating into the ground, more than 80% in general. And the very small part is just by runoff evacuated, which is absolutely the the reverse pattern for a very urbanized area, like a business district, where you have very low infiltration in the soil and high water available for evaporation immediately, for example. And between forest and business district, you have pasture that infiltrate more than urbanized area, but less than the forest. So for the land-water balance, we have this equation. So the soil moisture content of the soil is the input, precipitation, minus the output, so evaporation, and the sum of runoff, surface runoff and groundwater runoff. You can see that directly the land use and land cover changes affect the evaporation and the evapotranspiration efficiency. But indirectly, you can also have different cloud cover, and that can feed back with different precipitation and different evapotranspiration. And of course, these two cycle, energy and water cycle, are coupled through mainly the evaporation. So we will see now how these different biophysical changes account in the temperature changes due to land cover or land use changes. If you have to remember, I think one thing is that you have three main biophysical changes. And a forest, it's dark, it's transparent, and it's rough. So it implies changes in albedo, in evapotranspiration efficiency, and in roughness length. Let's see now the figures there of forested on the left and deforested areas on the right. So a forest is darker, so it has a lower albedo than a grassland, for example, or a deforested areas. Then the reflected sunlight is higher for a deforested area, so it contributes when you deforest to cool the surface. For the transpiration efficiency, the ability of a forest to evaporate is higher in general than a deforested area, because you have a large water holding capacity, rooting depth, and leaves that allow this capacity. So when you deforest, you cut this ability to evaporate efficiently. So it contributes to warm the surface. And finally, the roughness length favors the turbulence in the case of the forest. So it contributes in general, when you have a forest, to increase the amount of turbulent fluxes. So when you cut the forest, you cut this ability in general to exchange these turbulent fluxes, and then you warm the surface. Okay, so that's the basic properties of biophysical changes. Now we will see in a idealized global deforestation modeling experiment the contribution, the relative contribution of these changes to the temperature changes. So that's a study from Davin and Denoble in 2010. And they have basically two simulations. One with a maximally forested world, where they first extend the dominant tree type of a grid cell to 100% of the grid cell. And second, it's made in a coherent way, in the sense that you don't put trees where you have a majority, I think 80% or more of bare ground. So you don't put trees where there is desert. And a second simulation where you just simply cut all the forests on Earth and you replace it by grass, C3 and C4. So you can see here the changes in leaf area index, which is basically the leaf area per ground area unit. So in the case of forest, you have large LI, especially in the tropical forests. And it's dramatically decreased when you put grass instead. And in general, the LI is diminishing. So let's see now the first impact, the first biophysical impact of this deforestation. So we have seen that the prevailing paradigm is that when you deforest, then you increase the reflected sunlight, then you will cool the surface. Well, this is exactly what we see. This is the changes in albedo after a deforestation. So you increase the albedo globally, and especially in boreal regions. So why that? Because the contrast between in albedo between a forest with snow and a grassland with snow, you can see it's even in Garmisch now. The albedo with a forest with snow is still low, whereas for a grassland with snow, it's very, very bright. So you have an amplification in boreal regions of the contrast in albedo when you deforest. This is why when you deforest, then the albedo difference is higher. And as it is a radiative forcing, then you see that the changes in annual temperature is quite proportional, and you have a cooling effect, especially in the boreal regions due to the presence of the snow. That's the first biophysical impact. The second one we saw was the evapotranspiration efficiency changes due to deforestation. So the prevailing paradigm is that when you deforest, you cut the ability for the land type to evaporate efficiently. So it will warm the surface, it will cool less. When we look at the difference between the two simulations in terms of turbulent fluxes, then the sum of turbulent fluxes is reduced because you reduce the evapotranspiration efficiency. And then it leads to warming, as expected, of the annual temperature globally, and especially in the tropical forests that are really good to evaporate and exchange latent heat flux with the atmosphere. Now the third biophysical impact was about the roughness and the change in roughness length. So when you cut a forest, the prevailing paradigm is that you basically reduce the turbulent fluxes, so you contribute to warm the surface because you have less turbulence. And this is exactly what we see here between the two simulations. We have a strong reduction of turbulent fluxes, especially where the forests are really rough, so in the tropics. And it leads to a warming, as expected, globally. Okay, so let's recap. The land use is also altering biophysical properties. That's a major innovation we can study now in land component, because SEMI5 model now include the land use effects, agriculture changes, urbanization, afforestation, deforestation, etc. And we have three major biophysical land properties changes. The albedo, when you deforest, you increase the reflected sunlight, so you cool the temperature relatively. The roughness effect, with a forest you have an important turbulent transfer, which is less the case in general with a deforested area, so you contribute to warm the surface relatively. And the evapotranspiration effect changes because the forest have efficient root extraction of soil moisture, which is not so the case for the grassland or deforested areas. So you contribute here to warm relatively the temperature. So let's see now how these three biophysical changes are affecting the temperature, and if there is some changes in function of the latitude. So we will look at the bottom panel here of the changes in temperature between the two simulations, from the southern hemisphere through the tropics and the boreal regions on the right. So the albedo effect is the blue bar, albedo effect on temperature changes. The roughness changes effect is in red, and evapotranspiration efficiency changes in yellow. What we see immediately is that the albedo changes, that leads to a cooling when you deforest, is predominating at high latitude because of the presence of the snow. So it completely offsets the little warmings you can have with reduced roughness and reduced evapotranspiration efficiency when you deforest. Completely offset, which leads us to a regional cooling over deforested areas. But see that it's completely different in tropical areas, because the albedo effect, the albedo contrast due to no snow in general, is not so high, and it can be completely offset, or slightly offset, sorry, with the warming caused by the reduction in roughness and evapotranspiration efficiency. So you can have, with a global deforestation, a small warming over deforested area in the tropics. And between tropics and boreal, you have the temperate regions, where the sign is not is still controversial, but according to this simulation, it seems to give cooling, biophysical cooling, due to deforestation in temperate regions. Okay, so we can recap here. The albedo changes are a radiative forcing, so and it gives a cooling effect in the case of a global deforestation. Here, according to the simulation, it gives globally on land and oceans minus 1.4 cooling effect due to deforestation. The changes are over land, but also on other oceans. So I will explain in the next slides why, because it's not very intuitive why, if you deforest on land, a priori, you can have some impacts elsewhere, not on land. You have stronger impacts in cold regions because of the snow albedo masking effects, and that changes because it's a radiative forcing, the radiative balance at the top of the atmosphere. By contrast, the roughness and evaporation efficiency changes, so they tend to be reduced in the case of a deforestation. It leads to a warming effect of roughly, in this simulation, 0.5 Kelvin. So if you make the sum of the total biophysical effect due to global scale deforestation, we have -1 degree Kelvin for this simulation. The effects are localized on land, and we have stronger effects in tropical regions, and these are non-radiative forcing. It just changes the redistribution of energy into the climate system. So as I said, if all is deforested and replaced by grassland globally, the biophysical effect is a cooling of 1.5 degree, and it has to be added to the loss of carbon sequestration of biogeochemical effect that maybe Joe talked about. So for global deforestation, the biophysical effect is comparable, if we calculate it roughly, to the biogeochemical warming of global scale deforestation of 1 degree. So I consider here 400 petagrams of carbon released. I think it's the above content of carbon if we cut all the forests on the globe. If we consider that 50% is retained by the atmosphere at equilibrium, we have more than 90 ppm, which gives us, with the best estimate of climate sensitivity, roughly 1 degree Kelvin. So that has been calculated in other studies, recent studies, and it's roughly what I show here. So I said that the albedo effect could have some impacts elsewhere than in the deforested areas. This study is suggesting that the tropical deforestation can also have some remote effects, can cool extratropical regions. So why? The deforestation, it gives us more albedo. So you have less absorbed energy, less energy to release the surface fluxes. So in general, in the column, you can have less atmospheric water vapor. This is what they show here, for example, for the specific humidity. So in black, in function of the altitude, you have the difference between the two simulations. And we see that it's negative values, so you have less humidity. And you have also a tropospheric cooling for the black line. And it's mainly due to the albedo changes. So you have a tropospheric drying, tropospheric cooling, because also water vapor is a greenhouse gas. So that can lead to a cooling in other regions, as we can see there. But this is enhanced by probably the ocean and sea ice feedbacks that react in function of the changes in temperature, in humidity, in the troposphere. They tested here this mechanism. So in dashed line you have prescribed sea surface temperature, and here it's the surface temperature change in function of latitude. Prescribed SST means that your ocean is passive. You don't make it interact with the atmospheric temperature changes. Whereas with the solid line, you allow your ocean to interact with the atmosphere. So you allow it to react to the tropospheric cooling. And in fact, when it's interactive, When it's coupled, then you see a cooling. The ocean will cool after this tropospheric drying and cooling. So it will increase maybe the sea ice in northern latitudes, increase the surface of ice cap, more albedo, etc. So you have a cooling effect that is feedback with this ocean and sea ice. Okay, so we can see now whether, because it was a modeling experiment, whether these biophysical effects of land use and land cover change have been observed. And notably, I will show some results on temperature changes. So, first observational study you can find, it's ad hoc experiment and monitored sites. So this is a very typical experiment in the 90s where they made this bunny fence experiment in the southwest Australia, where they just cleared 13 million of hectares of native eucalyptus to grow winter wheat. So believe me, that this part is the winter wheat, and this part here, that's the native eucalyptus vegetation. So what we see immediately in the data, but also in this talkative satellite image, is that we have probably more boundary clouds over the native vegetation. So we will see maybe why. Pittman in 2003 proposed two main mechanisms to explain that. So when you decrease the vegetation, when you cut and you deforest to grow the winter wheat, you will increase the albedo. It will reduce the shortwave absorption and so reduce the net radiation. So you have less energy to release to the atmosphere through the surface heat fluxes. It seems to decrease the latent heat flux and the sensible heat flux. So for the decrease of latent heat flux, then you decrease, logically, the water vapor in the column, which leads to less formation probability of convective clouds above the wheat. And you have also decreased sensible heat flux that contributed to heat the boundary layer. But here you have then a reduced boundary layer heating. It's colder, then the air can contain less water vapor, and that's the same thing. You decrease the convective clouds due to the increase in albedo. Second mechanism, when you cut the eucalyptus to grow the winter wheat, you decrease the roughness length. So you will increase the aerodynamic resistance to release the surface heat fluxes, the latent heat and the sensible heat flux. Same thing, you reduce the water vapor, the air contains less water vapor, it decreases the convective clouds. So this is why maybe we have in this region more clouds above the native vegetation. That's one of the biophysical impacts. As observational study, you can also have, you can study pairwise sites. So what is it? That's two monitored sites of fluxes, temperature, etc., where one has been deforested, for example, or where you had land use, and another where you have native vegetation, for example. And if you monitor the two, then you can have a delta T, change in temperature. And supposing that they are not distant, then you can consider they have the same climate, and that the changes in temperature is only due to the land use or land cover change. This is exactly what they made in the Lee et al. Study of Nature 2011 with 37 pairwise sites at a lot of bands of latitudes, going from the tropics over there to the boreal regions through the temperate latitudes. And what we see is that deforesting in the boreal regions seem to lead to a cooling, which is in line with what I showed previously, because maybe of the albedo that is dominating. In the tropics, by contrast, you seem to have a relative warming when you deforest. That's a local warming. There is a weak evidence because we have 3 points here, 3 pairwise sites. And for the temperate regions, which is always a question if the deforestation would lead to a cooling effect locally or not, it seems that around 45 degree north, for example, France or Germany, we have, although a large variability, we seem to have more a cooling effect due to deforestation in temperate latitudes. And finally, we can generalize not only for pairwise sites this study, but with satellite data, because we have this very interesting product from Hansen et al. In Science 2013, showing the forest changes from 2000 to 2012. So we can see, for example, that in tropic areas, we seem to have a loss of forest in general from 2000 to 2012, the red spots. And again, in some Eastern Europe area there. So that's a very highly resoluted data. I think it's 30 meter. And there is this study from Romain Alcama, where at a 50 kilometer resolution, for each transition of forest, so for example, you have X% of tree cover going to Y% of tree cover, you have a delta T for a given year. You have a change in annual temperature. Then for each grid cell, they make the average among all the years of these changes, this forest loss or this forest gain. And they obtain this very interesting figure, which is the temperature, annual temperature change due to forest loss at each point on the globe. So that's the biophysical local effect on temperature of deforestation. And we see again the cooling effect of forest loss, of deforestation in the majority of boreal regions, but also in temperate, whereas it's not so evident depending on the longitude. And we find again this warming effect, especially in the Amazon basin. So this warming effect due to forest loss. What is interesting is that here it's the zonal average in red. So we have this cooling effect in boreal regions, and it seems to be offset in the temperate latitudes, the warming there. The interesting thing, that's the seasonality of that. In winter, we have the presence of the snow in the temperate and boreal regions, so we have a strong cooling due to the albedo dramatic increase in case of deforestation. which is not so the case for tropical areas that does not experiment seasons. And we have also a warming for the summer, so deforesting in temperate and boreal regions seem to increase the temperature in summer. So why that? Because in summer you don't have snow, so the contrast season albedo is not so important. So you reduce the cooling effect of winter. But also, with deforestation in summer, you will dramatically decrease the evapotranspiration efficiency of the forest that is green and with a lot of leaves, which is not the case in winter. There is no leaves in temperate and boreal latitudes, can summarize. So you dramatically decrease the roughness health and the evapotranspiration efficiency, especially in summer, which will lead to this warming observed. So this is a real concern for deforestation from a biophysical point of view for temperate and boreal latitudes, especially for extreme heat wave, for example. I don't know if I have time to. Okay. Yes. Maybe 5 minutes with the models. Okay, so I will just show that, and that's okay. Okay, so we have seen the biophysical impacts of land use and land cover change, the radiative, the non-radiative aspects, some observational studies, and now I will show some specific modeling experiment to see whether there is a sensitivity of these biophysical effects on temperature. A question is whether the biophysical effect of land use and land cover change on temperature depend on CO2 concentration. Because, for example, this study is for now, the sensitivity now. So what if we increase the CO2? This is a study from Pittman et al. In Nature Climate Change 2011. And they compare the biophysical effects of land use and land cover change in 3 regions, Eurasia, Asia, and Eastern US, for 2 seasons, spring and summer. And they made another simulation with an increase, a doubling of CO2. So when it's blue, it means that the biophysical effects on temperature is reduced through the increase of CO2. So it seems that in spring, the biophysical effects on temperature of land use and land cover change is reduced when you increase the CO2 concentration. And that's the opposite pattern, at least in Eurasia and Eastern US, which see an amplified response of biophysical effect at mid-high latitude with increased CO2. So why? In general, we have a biophysical cooling effect at mid-high latitude. We see that. But when you have more CO2, you perturb the snowfall regimes and the rainfall regimes. And in the case of Eurasia, with more CO2, you tend to have less spring snow. So you have a shift, a northward shift of the snowfall regimes with increased CO2. And so you have a lot of regions that act not like a boreal region, but like a tropical region. And we have seen that In tropical cases, the biophysical effect is warming. So this is why maybe in Eurasia and in eastern US, in spring, due to the changes in snow, due to increased CO2, you dampen the biophysical effect on temperature. For the rainfall regime changes, it seems that with more CO2, you will have more precipitation in the north region, in the northern regions in Europe. And we have also less precipitation in the south, it's already observed. But more summer precipitation in the north. So it will give more latent heat flux, more evaporation capacity. So it will, with increased CO2, contribute to decrease the temperature relatively, because more latent heat flux with CO2 increase. And this seemed to amplify then the biophysical cooling effect. So there is also in Asia not so much change, as you can see. It's only limited, I mean, this effect on mid-high latitudes. Asia, it's more, this region is more in tropical areas, so there is no so much season. So it does not react so much to the CO2 increase in terms of biophysical effect as the Eurasia or Eastern US regions. Second, if we look at other seasons, autumn and winter, we don't have so much amplification or reduction. And these two effects seem that for annual temperature, it does not change so much. But the changes of biophysical effects has to be studied in different CO2 concentration to see if this study is really showing the effects we see there.